to people who come to the 2 talks. Okay. Okay. So the second talk is mostly expository. It's about the N-body problem. So we start from the beginning. Let's start the story from Kepler. So Kepler proposed his 3 laws about the motion of the planets. So the first law says that each planet moves on an ellipse with focus at the sun. So the second law was that the area swept by the planet in unit time is a constant. So the second law is exactly the conservation of the angular momentum. The third law says that the size of the summa major of each elliptic orbit raised to power 3 divided by the square of the period is a constant. Okay, so these are mainly empirical laws. Okay, so but Newton's laws was totally different. So Newton, on the one hand, he discovered calculus. On the other hand, he had his mechanics. So he wrote down this equation. So the motion of each planet is governed by this equation. The mass times the acceleration equals to the force. So Newton successfully solved this equation, and its solution proves Kepler's laws. So Newton's laws was actually very different from Kepler's laws because the difference can be seen from many aspects. For instance, you know, I mean, you can talk about the 3-body problem using the Newton's laws, but you cannot do that for using Kepler's laws. But anyway, so Newton himself formulated the 3-body problem, and in particular, he studied intensively the lunar problem. That means the 3-body problem of the sun, Earth, and the moon. So the equation is on the right-hand side. He realized that the 3-body problem was very complicated. He was not able to solve that using integrals. So he said that this caused him a headache, but he never doubted that the 3-body problem could be solved. So he says that because for the 3-body problem, we don't not only have we think each body moves along some elliptic orbit, but they have mutual attractions. So the mutual attractions can perturb the orbit away from ellipses. Newton says that if it happens, then God is going to come to push them back to the elliptic orbit. So that means the science at that time is mixed with fictions. So the influence or impact of Newton's mechanics was tremendous. So there's one philosophy called determinism, which was spoken explicitly by Laplace. Laplace says that this paragraph was very famous in history. It's called the Laplace demon. It says that he says that we can regard the present states of the universe as the effect of its past and the course of its future. An intellect, or we say God, which at some moment would suppose he knows all the forces that sets the nature in motion, all the positions of all atoms. So suppose the intellect were vast enough to analyze all the data, he's going to get a single formula that governs the motion of everything in the universe, including the greatest body and the atoms. So if that happens for such an intellect, nothing would be uncertain, and the future is just like the past. So the philosophy is very, at least from the viewpoint of modern people, is kind of strange, but it's believed at that time. So Newton's mechanics has deep impact to science and philosophy. So, for instance, after Newton, before the 20th century, almost all great mathematicians worked on the N-body problem. So it also has impact on philosophy. For instance, the philosophy of Kant was clearly influenced by Newton. I'm not going to say much about that. Anyway, so yeah, so we know that there's the famous novel of three-body problem. So there's one I noticed that once in a philosophy book of Poincaré, he said that it's exactly the celestial mechanics that tells us that physical laws exist. The reason why I'm writing this sentence here is that I'm trying to say that in a system of a three-body problem, it's basically impossible for people there to discover there is such a thing called physical laws because it's so chaotic. There's no regular motions. Anyway, so starting from Newton, after about 200 years, people still believe that the three-body problem was able to be solved. So but the story, the situation ends at the time of Poincaré. So the story was like this: Poincaré was trying to compete for a prize called the King Oscar II prize in 1895. At that time, he was I don't remember, about 35, something like that. So this prize, the purpose of the prize was to promote a new journal. It's called, it's now this time it's known, very very well known journal, Acta Mathematica. But at that time it was very new, so it was not so famous. So Mita Leffler persuaded the King Oscar to celebrate his 60th birthday and to give this competition. So in this competition, there was one problem. The problem asks you to solve the problem of the stability of the N-body problem. So Poincaré chose this problem, and he wrote a paper. He submitted the paper to the committee, and he got the prize. But after he got the prize, his paper was published. But the referee told him that there's something that the referee was not able to understand. Then Poincaré thought about that. It turns out that there's a big gap. So the gap was so serious that the paper was totally wrong. So he just withdraw all the published journals and wrote a new paper and published a new paper. So he paid a lot of money on that. Okay, it's about more than 1 year of his salary. But anyway, so what happens in the work? What's the mistake? It's roughly like this. Suppose you have a hyperbolic fixed point. The point P. Hyperbolic means that locally there's some contraction and some expansion. So you see at this point, this is related to my previous talk. So this is basically the only thing that I understand. But anyway, so there's a thing called a stable manifold. That means points on this curve. So every point on this curve converges to the point P as t goes to infinity. But the points on the other curve converge to P as t goes to negative infinity. So if the system is integrable like the two-body problem, then the two curves should be the same. But if it happens in the three-body problem, if it's a non-integrable system, the two curves in general should split. They do not coincide. So once there's some transversal intersection here, let's call it Q, then you are going to see this complicated picture. The point here is that the Q is going to converge to P under both forward and backward iterations. So under forward iteration, it's going to converge to P exponentially. And on the other hand, because the problem of P comes from celestial mechanics, the map preserves the area. That means this lobe area should be the same under the map. So then you are going to see that when the orbit gets close to P, on the one hand, it's going to get stretched in the unstable direction. On the other hand, it's going to be contracted. So this lobe is going to get very, very thin and very long. So it's going to create new intersections. The new intersection is going to create further intersections. So the picture is very complicated, and it's robust. You cannot perturb it away. So that's the correct picture that Poincare discovered after making a serious mistake. So this is now we call it the chaos. So what's the point of this? If you have this picture, then what can you say? So the meaning of chaos is that if you have a small perturbation of the initial condition, you expect that the perturbed orbit should be close to the unperturbed orbit for a long time. But if you let your time go to infinity, you basically expect that. So whenever you have chaos, what's going to happen after a long time is that the two orbits are going to be very far away from each other. So for instance, in practice, if you want to make predictions using differential equations like the weather prediction, so we have the differential equation. We have a measurement of our data, for instance, humidity or whatever. But for whatever measurement, it's going to have some error compared with the reality. So the error, the point of the chaos is that if you have error, and even though your differential equation is deterministic, the error is going to be propagated. So it's going to become big error. So that means after some time, your prediction using the differential equation is not reliable completely. So that's why for the weather forecast, we can only trust it for 1 week. So after 1 week, it's not believable. So the reason is here. So there's another notion called butterfly effect. That means a butterfly in the South America, it's going to perturb the air so greatly so that there's a tornado in the North America. So that's an illustration of the idea of chaos. So Poincare discovered that there's such a thing in the three-body problem. Therefore, the three-body problem is totally different from the two-body problem. Okay, so in celestial mechanics, there's the following model that's quite interesting. It's called this Sitnikov-Alexeyev model. So the model is like this. Suppose on the xy plane you have some these blue particles. Suppose they are massive. They are on some elliptic orbit. So on the z-axis, suppose you have some massless particle or very small mass particle on the z-axis. So you can arrange the initial condition in such a way that the orbit, this red point, has the following behavior. That means it oscillates between the 0 and infinity. If you look at the position as t go to infinity, you take the lim sup, it's infinity. But if you look at the lim inf, it's actually 0. So that's some very strange behavior in the three-body problem that cannot be expected for the two-body problem. So that's this solution was constructed using Poincare's result. Okay, so in the study of the three-body problem, we actually discovered many new mathematics. So I think the most important impact is that after Poincare, we no longer care about finding all solutions to a differential equation. But before that, whenever you have a differential equation, you try to find these solutions. So after Poincare, what we do is that we know the differential equations are so complicated Therefore, it's not possible to find all its solutions. In order to do something, you first need to have some viewpoint. According to your viewpoint, you try to extract information from the seas of complexities. So, for instance, Poincare himself studied the N-body problem in his lifetime until his death. So, for instance, he made important contributions. There are many important contributions. One was the Poincare recurrence. Actually, this notion appeared in his wrong paper. In the wrong paper, there was this correct theorem. So this led to the ergodic theory, and nowadays it has important application to many other fields such as number theory. So in Poincare's research, he studied a lot. He worked a lot for trying to find periodic orbits. So this is related to his work on topology, because in topology, to define first homotopy group or the first homology group, you have to use loops. So maybe let me mention one important result of Poincare. That's called the Poincare's last geometric theorem. He proposed a conjecture before his death, but he was not able to prove it. So the result says that, the conjecture says that, suppose you have an annulus, and on the annulus you have an area-preserving map. The map twists two boundaries to opposite directions, and then there has to be two fixed points. So he published a paper on this conjecture. He drew many pictures. So, and this conjecture quickly attracted many people because before this conjecture, the only known fixed point theorem was about finding one fixed point, but this one was special. So, but it turned out that this conjecture was quickly proved by Birkhoff, and this made Birkhoff famous quickly. So, but after another half a century, this problem led to further development. Arnold proposed another conjecture, saying that it's called the Arnold conjecture. This led to the birth of the field of symplectic geometry. His conjecture says the following thing. Suppose the idea is like this. Suppose you glue two annuli into a torus. So then you expect some Hamiltonian map on this torus should have four fixed points. And why four fixed points? Because you consider the cell decomposition of a torus, you get four elements. So then Arnold made his conjecture. So every Hamiltonian diffeomorphism on a compact symplectic manifold should be like this. So that's the starting point of the symplectic geometry. But anyway, so there's another result of Poincare from where you can see the idea of some later topology. It's called a Poincare-Hopf. So suppose on a manifold you have a vector field, and so the vector field may have zeros, and each zero in a very small neighborhood you can define its indices. So the Poincare-Hopf says that if you add up the indices, you get the Euler characteristics. The Euler characteristic is some global quantity which can be defined using topology, but the zeros of the indices of the zeros of vector field is very local. So this already contains the idea of local to global. So for instance, as Chen Jinxin's famous proof of the Gauss-Bonnet in higher dimensions, this appears in the last step, this theorem. Anyway, okay. So nowadays we also pursue periodic orbits. So one remarkable result was due to Shansini Montgomery, and actually this result also appeared in the book of Liu Cixin. So the result says that you can consider three particles with equal masses. They move on a figure 8 configuration. So this is a special solution to the three-body problem. So it's it led to further discoveries. So maybe I just show you some examples. Here, there's this figure cannot move because it's a PDF file. You can see there are many complicated three-body problem periodic orbits and the four-body problem and many body periodic orbits. Maybe anyway, let me skip that. So let's talk about next theme. So after Poincare, so in about the last 50s, there was this classical result called the KM theory. So the idea is as follows. In KM theory, you don't care about the periodic orbits. Instead, you care about quasi-periodic orbits. So you consider the N-body problem of our solar system as some Kepler problem. Each body moves around the sun along a Kepler orbit. Then you treat their mutual interaction as perturbations. Then suppose you ignore the perturbations, then each orbit is moving on ellipse, so it's periodic. So you know everything because two-body problems are integrable. But you add the perturbation, the problem may be very complicated. For instance, there's in the KM theory, there's a notion called resonance. For instance, in this picture, there are some just some satellites of the Jupiter. Its period has some this kind of linear integer relations. So if this happens, we call it a resonance. The theorem of the KM says that if your system, your unperturbed system, does not have this resonance, then for small perturbation, the perturbed system is also like this. So the perturbation does not destroy your motion. That means these particles moves around the sun quasi-periodically. Okay, so this theorem tells you that there is a almost full measure set of initial conditions on which the dynamics is quasi-periodic and it's stable forever. So this is an important result after Poincare. Okay, maybe let me go to the next theme. I'm just making preparations for my later part of the talk. So let's start with let's next consider the Painleve conjecture that I mentioned in my title. So we consider the general Newton N-body problem. We think it as some dynamical systems. So the idea of a dynamical system is roughly speaking to study the asymptotic behavior of a system as t goes to infinity. So if we adopt this idea, we consider this differential equation, we find that we can classify its solutions into two types. So there are basically, you don't care about the existence and uniqueness because they are trivial. But you care about if your solution is defined on a finite time interval or is defined on the entire positive real axis. So if the first case happens, for instance, if your equation is like x dot equal to x squared plus 1, then your solution is only defined on some finite interval. You call it a singularity. So if your solution is defined on the entire real axis, you call it global solution. The question is that what happens for the Newtonian N-body problem? So the question was first raised by Painleve. He was again invited by King Oscar II, and he to give lectures to in University of Stockholm. And at that time, Mita Lafleur was the president of that university. I had to mention that Painleve was actually more famous for his work as a politician. He worked twice as Prime Minister of France, and I think he's related to us because he's among the few great mathematicians who came to China in very early. For instance, he came to China in last 20s, about 100 years ago. So there are only very few mathematicians did that. The names that I knew was Russell, Vienna, Adama, and he was one. And he actually he liked his trip a lot. And but at that time he was already a politician. When he went back to France, he built a center for communication between China and France, the cultural communication, and himself served as the president. And the center still existed nowadays. So anyway, his question was that if you can find those singularities that does not have collisions. So we know collisions gives you singularities, but can you find any solution which only existed for finite time, but the solution blows up? The solution does not exist after finite time. So he proved that when n equal to 3, all solutions are collisions. All singularities are collisions. But so the question was really for what happens in the case of n greater than 3. Okay, so the conjecture was raised in 1897. So that's about 2 years after his lecture in Stockholm. I was very impressed by this. Actually, he after 2 years of his lectures, he wrote a manuscript. He published his lecture notes. I was very impressed because we can still find it. It's a lecture notes of 600 pages of handwritten, very beautiful handwriting. So, okay. Anyway, so after about 10 years of this conjecture, another mathematician. Actually, I should say he's not really a mathematician, but anyway, he studied with Painleve and Painleve. Von Zippel proved the following theorem. It gives a characterization of the non-collision singularity. So it says, suppose there is such kind of thing called non-collision singularity. Then when time goes to the singular time, you look at the maximal distances between the particles, the lim sup becomes infinity. But if you look the lim inf, it goes to 0. That means the particles has to get arbitrarily repeatedly very close to each other in order to get close to collision in order to exchange energy. On the other hand, they have to escape. Otherwise, if they are restricted in a compact region, they have to collide. So the two behaviors has to occur infinite many times within finite time interval. Okay, so this singularity is very special. Moser had the following sentence in his ICM talk in 1998. So that's the first talk in the ICM. Anyway, so he said that in general, when we talk about singularity, we always think it's some local behavior, but the non-collision singularity is different. So when a non-collision singularity occurs, it's non-local, it's wild, it's highly counterintuitive. So maybe I just give you some idea why Painleve made this conjecture. Actually, he didn't say why he made the conjecture, so I can only guess. So I think it's related to his work on the Painleve equations. After his lectures from the University of Stockholm, he made another contribution. Actually, I think this should be considered as his best contribution to math. He classified all the second-order ODEs whose only movable singularities are posed. That means you consider an ODE, you think its time t is defined on the complex plane. Then its solution is some holomorphic functions. So it should, in general, it has singularities. Then you change the initial condition. You find that the singularity should move. So he only wants the movable singularities are posed. Then he classified all these equations. There are totally 50 such equations. And among the 50, there are 6 of them that are most important. And among the 6, the last one is the most important one. So the Painleve 6 equation is the following one. And for this one, the only movable singularities are 0, 1, and infinity. So I think from here, it's quite natural for him to expect that the N-body problems equation is so complicated that it should make some essential singularities. So essential singularities are exactly non-collision singularities when projected to the real space. Okay, so we also know that whenever you have an essential singularity, according to the Picard-Gray theorem, it tells you that any neighborhood of the singularity is mapped to cover the entire complex plane for infinite many times, except for one point. So that's why you have the behavior of this von Zippel. Anyway, so the question, there's another thing. So if you are able to construct a non-collision singularity, you expect that you just add some remote body, you form a 5-body problem, then you get a non-collision singularity for 5 bodies. So the problem is really, the most difficult part is really the n equal to 4, the borderline case. So maybe let me just state a result that I obtained in this prize-winning paper. So actually, in this paper, I constructed non-collision singularities. So I'm going to show you another example that I constructed recently, but that's much simpler. So it's not moving. Anyway, let's skip this. So actually, with dog fiat, actually that was my thesis, but it's published later. So we constructed a simplified model. So suppose you have 4 bodies. There are 2 bodies that are fixed. We call it Q1 and Q2, and you put 2 smaller bodies in the system. One is moving around Q2, the other is traveling back and forth between the binaries. Then in this model, we constructed a solution which has velocities that blows up to infinity within finite time. So it's actually some highly non-trivial result because it's known to Ola that the two-center problem is, that means if you consider one particle moving in the gravitational field of 2 fixed centers, it's actually integrable. So, but our result says that you add 1 more body, it's actually very, very different. But anyway, so we recently with Gerver and Guan Huang, we constructed another model that's actually very simple. The idea is as follows. In this model, you can consider 4 equal mass particles. Suppose, there is a binary moving in the middle. So, so there are 2 others moving off. So this binary moves very fast. Suppose it catch up with this body. At some point, they form some equilateral triangle. So almost equilateral triangle. So we know that equilateral triangle is some stable configuration. That means once it's equilateral, it's going to be always equilateral, but the size shrinks. If you came to my last talk, actually, this thing is exactly correspond to the shrinker in the mean curvature flow. But anyway, so when you have when they get close to some equilateral triangle, then the equilateral triangle shrinks. Then they come to small scale. But we know that there's a potential energy that's negative. So the potential energy is going to become very negative, but the total energy is conserved. That means the kinetic energy is going to become very big. So at some point, because they are not exactly equilateral, so when they come to small scale, so when the scale is small enough, then they are no longer look like equilateral triangle. Then they are going to escape from this configuration. So what happens is that the binary is going to become a smaller binary. They are going to be expelled to the other direction very quickly. So because they get some large velocity. When the binary comes to here, then the same thing happens. So the binary gets accelerated again. So the same thing happens for infinite many steps, so you find that within finite time you can construct a non-collision singularity. So that's the idea in this work. So maybe let me briefly make a comment about this thing. So what I can say is that the existence of non-collision singularity is means the Newtonian mechanics has some intrinsic pathology, because we have to guarantee that the motion lies in the Euclidean space and time, and we have infinite velocity, and we also have the action at a distance. But all these are impossible. Also, we need to require that each particle is a point with no volume. So these things are not real, not realistic. Okay, so maybe let me briefly say something that what we can get after the conjecture is proved. So when a conjecture is proved, it's better that we can go beyond that. Otherwise, it's just useless. Okay, so concerning the global dynamics of the N-body problem, there are two major conjectures. One says that the set of singularities has zero measure. The other says that the set of singularities is a first category. So that means generically there's no singularity. So they are hard, so let's assume they are true. Let's proceed. Okay, suppose they are true, then we expect that we can talk about, for generic initial condition, what happens as t goes to infinity. So it's already studied by Shazi 100 years ago. He classified all the possible behavior as t goes to infinity for the three-body problem. So they are as follows. So you first consider two-body problem. You have hyperbolic motion, parabolic motion, and elliptic motion. Then if you have three bodies, you consider all the possible logical combinations of hyperbolic, parabolic, and elliptic. So the first case means that all the three bodies can be hyperbolic. That means as t goes to infinity, they move almost linearly. And it may happen that one body is hyperbolic, one body or two bodies are parabolic. So that's the second case. You just do all the possible combinations. You get totally 6 cases. But there's one more case. That's the oscillatory motion that I showed you before. So in the three-body problem, there's this strange chaotic motion. So Shazi says that, okay, they are everything. As t goes to infinity, there's no other possibilities. Then, but there's no further results in the past century in this direction. I think one reason is that you don't want to do the same thing as for 4-body or 5-body, because as the n gets larger, the problem certainly becomes more and more complicated. Okay, but moreover, I just want to convince you that if you want to say what happens, for instance, there are totally 7 cases. If you want to ask which case has positive measure, which case is dominant, which case has 0 measure, they are always very hard. So if you only look at bounded motions, there are many possibilities. It's basically impossible to get a clean classification. What I propose is to consider, instead of measure theoretical generic, just to consider topologically generic. So there is a classical conjecture. It's called the oldest problem in dynamical systems. So the conjecture was formulated by Birkhoff. Later, I don't really understand why Kolmogorov's name appears. But anyway, the conjecture says that the set of non-wandering points is nowhere dense. Then we have to define what is non-wandering points. It's just the set of points that just repeatedly come back, something like that. But anyway, so the conjecture tells you that the opposite case, the opposite case of nowhere dense is generic. So the generic case should be wandering. So the orbit just goes away, never comes back. So if the conjecture is true, that means that in the topological case sense, the N-body problem should be unstable. So all the above mentioned bounded motions like periodic orbits, homoclinic, or invariant torus, I mean the quasi-periodic orbits in the KM theory, they should be all non-generic. So from the eyes of a topologist, you just cannot see them at all. So, there's a bad thing about the conjecture. The conjecture does not give you a good conjecture for the final motions. So I made the following conjecture. I think it's very plausible, and I believe it's worth pursuing. So we consider what happens for generic initial condition. The conjecture says that the only possibility are those coming from the two-body problem. So as t goes to infinity, you look at the motion of each body. It either moves asymptotically linearly, that means it's hyperbolic, or it approaches Kepler elliptic motion, and with another body. That means there are two bodies, they form a pair, and the center of the pair moves almost linearly, and the binary approaches Kepler elliptic motion. That means if it's true, that means the N-body problem itself is very complicated, but it's nonlinear. So the nonlinearity, if you give it enough time, the nonlinearity is going to decouple the systems. So in the limit, the system should be much simplified. The only thing you expect in the limit should be Kepler motions. So I think this should be the ideal picture, but on the other hand, I think it's extremely hard. So then we can still say something about the final motion for the N-body problem. There's another result by Masha Sarre. You can consider this result as a strong support for my conjecture. It says that as t goes to infinity, in the N-body problem, there are two possibilities. One is that it's a super hyperbolic orbit. That means you look at the diameter of the system. As t goes to infinity, the diameter grows super linearly. So that means the diameter divided by t goes to infinity. Because we know that hyperbolic orbit grows only linearly. So they expect there's such thing that grows super linearly. And if it's not the first case, then the system should get decoupled into some subsystems. Each subsystem moves linearly away, and each subsystem expands like t to the power 2 over 3. This t to the power 2 over 3 is a parabolic behavior. So you expect parabolic behaviors are rare. So based on this result, if you know that super hyperbolic orbits are rare, then you basically expect my conjecture is true. So this theorem left open another question. So is there such a thing called a super hyperbolic orbit? It's just a concept. Does it exist? So with Guan Huang, we constructed another model saying that yes, it's true. In this model, the mechanism was the same as the last one. So there's a binary, and this particle is going to get close to the binary. When they get close to some equilateral triangle, the equilateral triangle shrinks. So the shrinking is going to accelerate Q1. So later Q1 is going to be expelled. Then when it comes to here, it turns around, then come back again. So in this model, there exist both non-collision singularities and super hyperbolic orbit. So that, the basic idea is that you think super hyperbolic orbits as some slower version of non-collision singularities. So in PDE, people say that you have finite time singularity or infinite time singularity. So here, super hyperbolic orbits are infinite time singularities. So with this idea, we prove this thing exists. And maybe I don't want to go to details. The point here is that you have some mechanism to study triple collision, near triple collision. So this is called the triple collision blowup. But so finally, I just mentioned with the existence of super hyperbolic orbit, we make another conjecture in our paper. So this conjecture gives you a picture about what happens for the final motion for the general N-body problem after Shazi. So the conjecture says that if you consider the N-body problem as n greater than or equal to 4, you look at all the possible final motions. The motto of with two-body problem, you have only bounded, hyperbolic, and parabolic. With three bodies, you have one more called oscillatory. And with the four bodies, you have super hyperbolic. And then you consider more bodies, you don't see anything new. So basically, the idea is, the point of the conjecture says that if you understand the four-body problem, you basically understand the N-body problem if you only care about the final motion. So so I think it's something worth of pursuing. Anyway, so if I make a conclusion, I should say that the N-body problem should be considered as the simplest complex systems. So it's simple enough to simple means that our solar system is nearly integrable. So the motions are roughly periodic. So then living on Earth, we know there's such a thing called physical laws, but they are so complicated that it's hard to completely understand them. So it tells us that our nature and mathematics are very complicated. So we have to do researches without end. So this chaos or this complexity also tells us there should be such a thing called free will. It's not completely determined as said by Laplace. Okay, I think let me stop here. Thank you very much. Okay, are there any questions? 主持人不在了，我们可以放飞了。Generic 就是 countable intersection of open dense sets. Countable 对。The Bayer second category. 哪个例？它是这样啊，我最早那个文章是要有2个非常小的质量，然后我后面的就是要有限制，但是就是。对，我现在做的都要限制在平面上，然后空间上也能做，但是技术上更复杂，然后我是没有意愿再去做它，对，它都在一个平面上，它不会exactly 在一条线上，它这条线它 eventually 会 approach 一条线。你数一下哈，就是每个粒子现在都在平面上，2个维数的位置，2个维数动量，对吧？就是4乘4等于16，坐标就是2维的嘛，坐标是2维的，对，在2维平面上嘛。对，但是我们要动量和位置同时考虑，所以就是16你要磨掉平移对称，磨掉旋转对称，最后剩10个。对，就是动量守恒和角动量守恒。不垂直，你没有办法保证它一直垂直。就是我这个画是看上去是那 Q1 Q2 在一条线上，但事实上等它跑起来的时候，它没有办法保证它在一条线上。啊，对，就在这平面上，对。对。 我想是对的，就是我想应该不是很困难的 conjecture， 不过是没人去做它。但是我不知道怎么做啊。对，需要有人花时间去想，我不知道怎么做。对。哦，这种情况是吧？啊，这种应该没有人做过这件事情。对，是的。但是你要是假设它有体积的话，会有些工作。我这儿没有体积，它要撞到一起了就按停了。哪个 category？我这个，比如说这个例子，全部速度都是无穷大。对，它是在最后那一个 moment， 就是那个就是那个时间点，就是那一个 time moment， 这个需要在那个0的长度的时间区间来回要跑无穷多趟，它的速度是无穷大。对，这些都要无穷大的速度往无穷远跑，然后在无穷远处它们都是碰撞了嘛，然后这个 Q2 以非常大的速度往那边跑，然后这个就是你的时间越靠近的那个 singular moment 的话，这个跑得越快，所以它会在最后那一个时刻，那一个 moment， 那个0长度的时刻，那个 Q1 要来回跑无穷多次，它走的那个路程一趟就是无穷大，然后要跑无穷，就 highly singular， 对。全都是无穷大，对对，全是无穷大，就这个前面这个也是，都必须是这样，没有办法，对，必须是。然后这个对，反正是一个 highly counterintuitive 的。